Good morning, everyone. Today we are going to explain part 2 of chapter number 8. Our agenda today is to explain diesel cycle, then solve one example to understand the idea of diesel cycle, then we'll explain dual cycle, then the last part, Stirling and Ericsson cycle. So diesel cycle, the difference between diesel cycle and the Otto cycle is about the spark plug. In the Otto cycle, we have the spark plug to get the ignition, while in the diesel cycle, we will have to compress the whole fuel up to reaching to the auto ignition, and this part it will help to remove the engine knocking inside the system as we have explained in the previous part. So the difference here in the compression ratio between the diesel cycle and the Otto cycle, it will be around 12 to 24, which is the diesel cycle is lower than the Otto cycle. In the diesel cycle, we have the cycles between point number 1 and point number 2. We have a compression area. In the last part, in the Otto cycle, between point number 2 and point number 3, we have a compression area, so it will be getting the ignition at point number 3. While here, between point number 2 and point number 3, we will have to get the auto ignition. So in this part, the pressure will be remain constant, while the temperature at point number 3, it will be much higher than point number 2, based on the TS diagram. So at this part, we will have the heat in and heat out, and between point number 3 and point number 4, we will have the isentropic again. So according to this one, we may able to calculate the whole kind of the calculation based on the data provided of point number 1. So point number 1, the question will be able to provide for us as a whole data from pressure, temperature, and whatever information from the compression ratio and so on. Then we will be able to calculate point number 2 after the compression. Then we will use the idea of the constant pressure to calculate the rest of the information point number 3. Then we will be able to calculate point number 4. Then the formula that we are able to use in this part of the calculation, we have heat in negative with the work out, then it will be equal to the differential of the internal energy between 3 and 2 as inside the combustion part. So at the other part, we have the negative Q out. It will be equals the internal and the differential of the internal energy between point number 1 and point number 4, as we have explained earlier in the diagram. So between point number 2 and point number 3, we have the constant pressure. So in this part, we will have the heat in is equals the work, as have we explained in chapter number 3, that the pressure it will be multiplied by the differential of the specific volume between point number 2 and point number 3, plus the internal energy, well, both of them inside the combustion area. Also, it will be equals the differential of the enthalpy, or it will equals the Cp multiplied by the differential of the temperature, and don't forget to multiply by the mass. While the heat out is equals the differential of the internal energy between point number 4 and point number 1, while here we have constant volume, so it will be mass multiplied by constant volume multiplied by the differential of the temperature. The efficiency of the diesel and the efficiency of the Otto cycle is only about the location of the combustion that we are looking for. So all the equations will be remain same, nothing it will be different. The new here in the diesel cycle, we have compression ratio, and also we have cutoff ratio. The compression ratio, it will be between point number 1 and point number 2, while the cutoff ratio, it will be between point number 3 and point number 2 in the combustion area. The efficiency of the auto, it will be higher than the efficiency of the diesel based on the spark ignition and the calculation. Then the K, which is the constant, as I have mentioned earlier in the previous part, it will be equals 1.4 in our calculation. This example, it will help us to understand the idea of the diesel cycle. This example is by British unit, but we will focus on the procedure, not on the units. So an ideal diesel, so from the question, we have the ideal diesel, so we will have to use the ideal equation if it will be required in our calculation. So ideal diesel cycle with air as a working fluid has a compression ratio of 18 and the cutoff ratio is equals to. At the beginning of the compression process, the working fluid is equals, we have the pressure is equals 14.7, temperature is equals 80, and the volume is equals 117. Utilizing cold air standard, then the question is looking for temperature and pressure of each, or at the end of each process. So we would like to calculate point number 1, 2, 3, and 4. Usually point number 1 is provided in the question. Then we need to calculate point number 2, 3, and 4 based on the formulas. The other part, we have to calculate the net work output and the thermal efficiency. So once we find all the information from temperature and pressure at each point, it will be easy to calculate heat in and heat out to calculate the work net. Then we'll be able to calculate the thermal efficiency based on the W net over heat in. Then at the last part is the mean effective pressure. As I mentioned in the previous time, that the mean effective pressure is the last point of your calculation. So in the beginning, we will be able to calculate the volume number 2 from the formula of the compression ratio. So it will be volume number 1 over compression ratio to be able to calculate volume number 2. Then volume number 3 we'll be able to using by the cut-off ratio. Then we'll be able to calculate specific volume number 4, which is a constant as same as volume number 1. So between 1 and 2, we'll be able to calculate temperature number 2 based on the formula of the ratio between the temperature and the volumes. So we'll use the compression ratio in our calculation, which is power k negative with 1. Same with the pressure, which is the compression ratio with power k. While pressure number 2 and pressure number 3, based on the idea of the diesel cycle is equals same, then we will use the ideal gases equation based on the constant pressure. So we have the ratio balance. It will be between the pressure volume over temperature for both of them to calculate temperature number 3. So once we will be able to calculate temperature number 3, we will use the equation of ratio of temperature the ratio of the temperature and the ratio of the volume between the 3 and 4. Then we will use same idea of the pressure number 4. So once we calculate all the information between the temperature and the pressure, we will be able to calculate heat in and out. So before starting to calculate the heat in and out, we have to calculate the mass to be able to calculate the equation based on the ideal gases. So the heat in and heat out will be calculated based on the MCP delta T between the combustion area 3 and 2, and the out between the constant volume between temperature number 4 and temperature number 1. So by calculating the heat in and heat out, we will be able to calculate the W net. Then by finding W net, which is the differential of the heat in and heat out, we'll be able to calculate the thermal efficiency as I mentioned earlier. Then the last part, which is the mean effective pressure, which is the W net over the differential of the volumes. Dual cycle. Dual cycle, the difference between dual cycle and the rest of the cycles that we have explained earlier is a combination between the diesel cycle, the diesel cycle and the Otto cycle. Usually between point number 1 and point number 2, we have a compression area. So both of them to be remain same as the isentropic. So we'll come after the compression of the whole area, we will have Otto cycle that between point number 2 and point number X, which is the ignition part. Then we will have point X at point number 3, we will have compression part. So we have here 2 heat in and 1 heat out. Then we have another isentropic, then up to reaching point number 4. Then we'll be able to calculate the rest of the calculation from the W net. The last part, which is the Stirling and the Ericsson cycles. Here we have Carnot cycle, Stirling cycle, and the Ericsson cycle. As I mentioned earlier, we have a Carnot cycle, which is the ideal cycle that has no friction, has no heat increasing. There is nothing, it will be affect the whole system as perfect. The efficiency, it will be the highest. So in this part, we have between temperature number 1 and temperature number 2, it will be constant temperature. Then we have heat in and heat out between 3 and 4 as usual for the rest of the cycles. Then we will have between point number 2 and point number 3, we have a constant isentropic. Then we'll have another isentropic between 4 and number 1. So this cycle, it will be shaped as a square shape, while the rest of the curving shapes between Stirling and Ericsson, the difference between both of them is about the part of the constant. Here we have constant volume, and here we have pressure constant. So according to this one, we'll be able to calculate the high temperature and the low temperature for both of them to be able to calculate the efficiency provided. So this part we have explained just earlier based on the diagrams as provided. So we will have the based on the state 1, state 2, state 3, state 4, and this is the description that I have explained just earlier for the Stirling and the Ericsson cycle and what's the difference between all of them. So in this part, we will have the turbine that will be heat in to be moved as high heat. Then we will remove until the generator. Then it will move out up to the constant compressor to get the heat out, while the work net will be between both of them. So the efficiency for the Stirling, Ericsson, and Carnot cycle will be equals 1 negative with temperature number with the low temperature over the high temperature to be calculated the efficiency required in the question. Thank you.